Max Brown, the science clown.
Max. Max
Brown, the science clown. Physics rules. Max Brown, the science clown.
Max
Brown, the science clown.
Max Brown, the science clown.
Light. What is it really? Light is a particle that acts and travels like a transverse wave.
As you can see, as light waves travel, the magnetic and electric fields oscillate perpendicularly. Their troughs and crests align and also reach equilibrium together. The wavelength is equal to the distance between two identical parts of the wave. Waves, such as light, can also be described by the equation velocity equals wavelength times frequency.
You see, unlike sound, which is a wave that expands and contracts like this, light is a transverse wave, which goes up and down like a string. Like a string, light can only go in one direction, whether it's brought like a flashlight or focused like a laser.
But the direction of light can change.
When light travels through a new medium, it refracts. You can observe refractions in cameras, water, or a magnifying glass. To draw a ray diagram of refraction, there are 3 rules. 1. A light ray passing through the center of the lens is not deflected at all. 2. A light ray parallel to the axis passes through the far focal point. 3. A light ray passing through the near focal point emerges parallel to the axis. From this, you can see where the image is located, its orientation, type, and magnification. The location is just where any 2 lines intersect. The orientation is determined by where the image is located. If it's below the x-axis, as with this example, then the image is flipped and is known as a real image. If the image is above the x-axis, it's upright and known as a virtual image. If the object is beyond 2f, or twice the focal point, then the image is smaller. If the object is at 2f, the image is the same size. If the object is less than 2f, then the image is larger. Reflection, thankfully, is much simpler. Draw your light particle hitting the mirror with an angle of incidence equal to the angle of reflection. An image formed through a plane mirror will be virtual, upright, but reversed from left to right. The speed of light in a vacuum is different from the speed of light in air, or water, or another medium. A vacuum, like a black hole in space, is dark because the light is faster in a vacuum. There is no matter resisting the movement of light particles. And all of this light is part of something called the electromagnetic spectrum.
All light falls in something called the electromagnetic spectrum, the range of waves and photon energies. The wavelengths of light, which are visible to the human eye, is called the visible radiation. The visible light spectrum falls from 700 nanometers to 400 nanometers. More than light, there's multiple regions of the electromagnetic spectrum. There's gamma radiation, like the Hulk, which are the most energetic form of electromagnetic radiation. They are the product of radioactive atoms, and they interact with material by colliding with the electrons in the shells of atoms. Their photons have a lot of energy, with 100 electron volts to 100,000 electron volts. There's X-ray radiation, like what you get when you have a broken bone. They're produced when electrons strike a metal target. Soft X-rays have comparatively high frequencies and relatively short wavelengths. Hard X-rays occupy the same spectrum as gamma rays. Still, these X-rays are produced by accelerating electrons, while gamma rays are produced by atomic nuclei. There's ultraviolet radiation, what you get from the sun. Ultraviolet light is a type of electromagnetic radiation which comes from the sun. Ultraviolet light falls in the range of the electromagnetic spectrum between visible light and X-rays. UV rays are divided into 3 sub-bands. The bands are UVA, UVB, or UVC. UVA is called near UV. UVB is middle UV, and UVC is called far UV. After these are vacuum or extreme UV. These wavelengths are blocked by air and they only propagate in a vacuum. UV radiation has enough energy to break chemical bonds. This is why when people go in the sun, they are recommended to put on sunscreen. There's infrared radiation, a type of energy that can't be seen but can be felt as heat. It's commonly used to find heat signatures and can be used to see in the dark. This is why there's such a prevalent use of infrared radiation as night vision goggles in the military. Everything with a temperature above 5 degrees Kelvin or negative 450 degrees Fahrenheit or minus 268 degrees Celsius emits infrared radiation. There's terahertz radiation, which are tight bunches of electrons at nearly the speed of light through a magnetic field. Their wavelength, shorter than microwaves, longer than infrared, corresponds with biomolecular vibrations. Terahertz radiation can pass through clothing, paper, cardboard, wood, masonry, plastic, and ceramics, but cannot pass through conducting materials. There's microwave radiation, which can be used for communications, radar, and perhaps most known to most people, cooking. They are considered to have the second longest wavelength and are very powerful. Microwaves have frequencies that stretch from approximately 3 billion cycles per second, or 3 gigahertz, all the way to 30 trillion hertz, and wavelengths of about 30 centimeters, or 12 inches, to 3 millimeters, 0.12 inches. And finally, there's radio waves, which are the most commonly used waves. We use radio waves for communication, television, cell phones, and radios that all individually receive radio waves and automatically convert them into mechanical vibrations within the speaker to create audible sound waves. Radio waves have the longest wavelengths in the electromagnetic spectrum. In wavelength and frequency, the equation wavelength equals speed of light over frequency. The higher the frequency, the shorter the wavelength. Because all light waves move through a vacuum at the same speed, the number of wave crests passing by a given point in 1 second depends on the wavelength. The frequency will be larger for a short wavelength wave than for a long wavelength wave. Finally, the photoelectric effect occurs when matter emits electrons upon exposure to electromagnetic radiation, like photons of a light. This effect defies the classical view of light as a wave. And now we're done with the electromagnetic spectrum.
The first practice problem that we have says, determine the frequency of red visible light with a wavelength of 650 nanometers. So 1 meter is equal to 10 to the 9th power nanometers. So that's really small. So we use the wavelength formula that we used from simple harmonic motion and waves, which is velocity equals wavelength times frequency. And if we solve for frequency, it's velocity divided by wavelength. So the velocity of visible light is 3.0 times 10 to the 8th meters per second. So the wavelength would be, and we convert the nanometers to meters, would be 6.5 times 10 to the negative 11th. And if you put that in the calculator, you get an answer of 4.6 times 10 to the 18th. And that would be your frequency. So the second problem we have says, determine the wavelength of blue visible light. And they give us a frequency of 6.1 times 10 to the 14th. So we use the same wavelength formula, which is velocity equals wavelength times frequency. And then we solve for the wavelength, which gives us velocity over frequency. We use the same velocity for the speed of light, which is 3.0 times 10 to the 8th. And we put that on top of the frequency which is 6.1 times 10 to the 14th, and you put that in the calculator, and you get 4.9 times 10 to the negative 7th. But for light waves, we want them to be in nanometers so that it's a little more accurate. So again, 1 meter is equal to 10 to the 9th nanometers. So if you do the dimensional analysis, it comes out to be 490 nanometers is the wavelength of blue visible light.
Welcome to Channel 9 News. I'm your host, Mike Current. There has been a recent surge in magnet-related incidents, so we will be covering what you should do in case you spot a magnet. But first, the weather. As you can see here, we have actually spotted 2 magnets in our area. We believe they were created by the movement of charged particles. Now, if you look right here, you will notice that there are 2 north poles. Since all magnets have polarity, and like poles repel while unlike poles attract, these magnetic forces will repel. That means the magnetic field lines will push against each other and be attracted to the south pole on the other end of their magnet. To find magnetic force, we will have to use the formula F equals QV sine theta, or force equals charge times velocity times B field sine theta. We have not yet determined which type of magnets these are: permanent magnets, whose domains are aligned, and temporary magnets, whose domains are only temporarily aligned. In order to protect you and your family from things like current-carrying wires, you must first identify the direction of the magnetic field. This is done by using the right-hand rule. The right-hand rule is done by grasping the coil with your right hand with your thumb pointing towards the positive current. Then wrap your finger around the wire. The direction of your finger shows the direction of the magnetic force. Another thing you must know is the strength of the electromagnet. There are a few things that affect the strength of an electromagnet: the number of coils in the wire, the voltage, the size of the core, and the metal used in the core. There are 2 ways for a current to be produced in a magnet. Either a wire is being moved in an electromagnetic field, or the magnetic field around the wire is being changed. However, if you move a magnet parallel to the field lines of the electromagnetic field, no current will be produced. That's all for now. Thanks for watching Channel 9 News.
Sitting in my chair with a plate of grilled bacon, call my homie Peyton just to see what was shaking.
Yo, Simon, our class is dope and litty, so check out how we learned about thermal energy.
They call it physics. What? It's thermal energy. Physics. What? It's thermal energy. Temperature is not the same as heat. They call it that because the average energy.
Energy goes from hot to cool. If you tend to think otherwise, then
You've been a fool. Higher temperature is higher kinetic, but that is real science. It's not theoretic.
There's only 2 laws you have to know. Now just sit down and
Watch the show. The first law, Q equals U plus W. Wait, check it out, yo. This is how we do.
When particles are heated, they go really wacky, but freezing an object makes them stop snappy.
Conduction's when you touch something hot, just like when you touch a burning hot pot. Hot, pot, hot, pot, hot, pot, hot, pot. Now that we've covered points of thermal energy, you have the knowledge to take on anything. They call it physics. What? It's thermal energy. Physics. What? It's thermal energy. Physics. What? It's thermal energy. Physics. What? It's thermal energy.
And now some modern physics roasts.
You're large and unstable.
Dude, Einstein's theory of relativity states that nothing is absolute, but that was absolutely awful.
Dude, whatever that roast was supposed to be, I just want a fundamental force you to stop.
Ooh. Listen, the door is over there, alright? This is me, gravitational waving you goodbye.
Oh, you must be gamma radiation, because you don't even matter.
Boom roasted.
Dude, listen, if you were a fundamental force, you wouldn't be strong, because you can't hold anything together. Wow. Your mama so ugly that she repelled all of the fundamental forces.
Your mom was so tiny, you could walk the plank just by walking over her.
Dude, your mama's so strange, she's a conserved quality.
Ooh. Your mom's so old, she started to break down before classical physics.
Your mom was so dumb, she doesn't know where she's going and still doesn't know where she is.
Your mom was so fat, she exploded and a neutron star appeared.
Your mom was so hungry, her stomach holds a black hole.
Oh. Your mom was so dumb, she just thought that mass decreased at relativistic speeds.
Oh.
You must be responsible for beta decay, because your roasts are weak.
Oh. The only thing weak here is your abuse of decay.
Ouch. Well, you're so sensitive, you can detect gravitational waves.
Wow.
If you were in a box that wasn't being observed, I would know you were dead when they opened it.
Oh. This goes so thick, even gamma rays can't get through it.
Dude, you're so lazy that energy does not convert in a nuclear reaction.
Dude, quit being so critical. It's like the universe has zero curvature.
Dude, if you're gonna come at me so weak, they might as well call you a gravitational force.
Wait, what am I doing?
Stop. What's it do that? Okay, let's go. The first law, QE.
Yeah, we're ready.
Can you give us a tutorial on how to tie this bow tie? Let's start over from the beginning.
You look like from like the 18th century.
The cravat.
Oh, ooh.
Oh, I don't know what I just did.
Good form.
Interesting. Wow.
Y'all are weird.
It says one
Ha.
bow tie.
Oh my gosh, that's so good.
It's not fair. I can barely tie
I
a
wish I
normal
was as
tie.
dapper as you, dude. Come on, man. That's
That's
cool.
awesome.
She repelled all of the fundamental forces.
You could. Your mom was so tiny, you could walk the plank just by stepping over her.
Wow.
See how fast I can move the camera and it's still weird.
Oh, the tie is off.
Gross. Like,
2, 1.
But the direction of light can change.
You right there, bud?